linear predictive analysis, LPA, also called linear predictive coding, LPC, or linear prediction, LP, is one of the most powerful speech analysis techniques, and one of the most useful methods for encoding good quality speech at a low bit rate and provides extremely accurate estimate of speech parameters. Consider from the time domain perspective, the output samples of a time-discrete linear system can be approximated by the linear combination of its input samples and past output samples. That is the linear prediction value. A unique set of predictor coefficients can be determined by minimizing the mean square value of difference between the actual output value and the linear prediction value. These coefficients are the weighting coefficients used in the linear combination. The expression of Sn by a series of sequences, Sn minus k, is just one form of linear regression. This kind of prediction is also called autoregressive model. There are three zero-pole models which are important methods for studying time series: AR, autoregressive model; MA, moving average model; ARMA, combination of AR and MA. The three models can be used for spectral estimation of stationary random processes. So far, the most commonly used model is ALPO model. For speech signal, the channel transfer function can be described as ALPO function, AR model. There are several reasons. First, it is the easiest way to calculate the ALPO model. Second, in most cases, it is impossible to know the input. Third, for speech signals, when nasal sounds and partial fricatives are not considered, the transmission function of the channel is an ALPO function. We can convert the transfer function Hz into time domain expression Sn by use of Z transform. If the input GUN can be ignored, Sn is just approximated by the past samples, which is called linear prediction. The speech production is described as AR model and represented with vocal tract parameters AK. The linear predictor is used to estimate the input sequences through linear predictive analysis with LP coefficients alpha k. After the input signal is filtered by the inverse filter AZ, it leads to prediction error. Alpha k are the filter parameters or linear prediction parameters. We hope that the linear prediction coefficients are selected very well. That is, alpha k equals AK and EZ equals GUZ. Thus, the speech analysis and synthesis procedures can be perfect. There are some methods to compute linear prediction coefficients, which will be introduced in next session. LPC methods have been widely used in speech coding, speech synthesis, speech recognition, speaker recognition and verification, and speech storage. LPC methods provide extremely accurate estimates of speech parameters. Does it extremely efficient? The basic idea of linear prediction is that current speech sample can be closely approximated as a linear combination of the past samples. From the view of mathematics, linear predictive analysis is a simple form of the first-order extrapolation. It can be used as a method of reducing the amount of data needed to approximately encode a series of values representing voice. LP is also based on speech production and synthesis models. Speech can be modeled as the output of a linear time-varying system, excited by either quasi-periodic pulses or noise. Assuming that model parameters remain constant over speech analysis interval, LP provides a robust, reliable, and accurate method for estimating the parameters of the linear system, such as the combined vocal tract, glottal pulse, and radiation characteristic for voice speech. The figure shows a simple system to produce voice or unvoiced speech. The time-varying digital filter represents the effects of the glottal pulse shape, the vocal tract, and a radiation at the lips. The system is excited when an impulse train for voice speech or a random noise sequence for unvoiced speech. Output model is a natural representation for non-nasal voice speech, but it also works reasonably well for nasals and unvoiced sound. LPC analyzes the speech signal by estimating the formants, removing their effects from the speech signal, and estimating the intensity and the frequency of the remaining buzz. The process of removing the formants is called inverse filtering, and the remaining signal after the subtraction of the filtered model signal is called the residue. LPC starts with the assumption that a speech signal is produced by a buzzer at the end of a tube for voice speech. The voice tract from the throat to the mouth forms a tube, which is formants. The vocal tract from the throat to the mouth forms the tube, which is characterized by its resonances, which give rise to formants. The values which describe the intensity and frequency of the buzz, the formants, and the residual signal can be stored or transmitted somewhere else. LPC synthesizes the speech signal by reversing the process, use the buzz parameters and the residue to create a source signal, use the formats to create a filter, which represents the tube, and run the source through the filter, resulting in speech. Because speech signals vary with time, this process is done on short intervals of speech signal, which are called frames. As is shown in the figure, AZ is an inverse filter for HZ, which is used to remove formants at a speech encoder. Speech decoder aims to produce the speech signal based on the excitation and the time-varying digital filter HZ. That's all for this session. See you next session.